again, so it's on the recording, the control layer practicum submittal 1 is due now. I pushed it back to Sunday the 13th at 11:59. You know, I don't want to do that on you know, I don't want to start doing that on everything. So, you know, do be aware of when stuff's coming up, when stuff's due, you know, and give yourself plenty of time to work on this stuff. You know, as we get into the semester, you know, try to get into a good rhythm of staying on top of this stuff, so you don't, you know, get up to deadlines and doing stuff at the last minute. That's never good for your stress and never good for your grades. Can everybody see the PowerPoint? Yeah, cool. Okay, again, we're talking about psychrometrics, and psychrometrics is the study of moist air, right? And here's a picture of the psychrometric chart on the top right. And engineers use this, and HVAC designers use this as like a quick reference tool that you know, it helps them define the properties of moist air during the processes that change the properties of that air. Okay, so you know, you've got we're dealing with sensible heat, which relates to temperature. Okay, remember, temperature is how we quantify kinetic energy. So sensible heat is temperature of the air, you know, without taking moisture into consideration. And latent heat relates to the energy involved with phase change. So the amount of energy that's in the moisture in the air. Okay, and here's the psychrometric chart. So this is the tool we'll be using when we're dealing with psychrometrics. And remember that the psychrometric chart is associated with a specific value for atmospheric pressure. You know, the chart is not going to be the same for Boone as the chart for somewhere on the coast or something like that. So again, we'll go over these parameters that are on the psychrometric chart. Dry bulb, there's my thing here. There we go. Ooh, that's handy. How did I do that? Oh, well. So we've got dry bulb temperature down here. And remember, your dry bulb, well, oh, there it is. Okay. Dry bulb temperature. So when you have a thermometer, normal thermometer, and you measure temperature, that's what you get. You're getting the kinetic energy in the air, not, you know, it doesn't take into account humidity, stuff like that. So dry bulb temperature. We've got relative humidity that's expressed as a percentage. That's on these curved lines. And remember that it's relative to the amount of energy that's in the air. So as air warms up, it expands. As materials warm up, they get more kinetic energy, they vibrate faster, they tend to expand, right? So when you have more energy in the air, that energy, you know, is sort of, as that gas expands, it allows the possibility for more humidity to be in the air. And as that gas cools down, as air cools down and loses energy, the humidity in the air starts to, you know, contract, I guess, or, you know, you start to lose humidity. So the relative humidity increases as air cools down. So warm air holds more humidity, cooler air holds less humidity. And then we've got dew point. So I screwed that one up. Dew point is TdP. So this is the dew point. This curved line here is the dew point all the way down here based on temperature and humidity ratio. So as I move up and down on the y-axis, I'm changing the amount of moisture in the air. Remember that. So latent energy is over here. Sensible energy is over here, if you can read that. As I move right and left, I'm just changing temperature. I'm changing the amount of kinetic energy in the air. Okay, so the dew point is the temperature below which water condenses. And then we've got saturation temperature, same thing as the dew point. When when air is saturated with moisture, it can't hold any more moisture. It's going to start to condense. So saturation temperature and dew point are the same thing. So then we've got wet bulb. And that, you remember, we talked about how a wet bulb thermometer works, or a sling psychrometer. Your wet bulb thermometer has a cloth, and when you sling it around in the air, the amount of humidity in the air is going to determine how quickly it evaporates. Okay, and then when it gets to the same when that thermometer gets the same temperature as the air, or less than that, cooler than the air is going to warm it back up. So that it gives us an idea of the relationship between the temperature of the air and the amount of humidity in the air. Okay, so then we have humidity ratio expressed as W. Sorry, still can't write with this thing. Lowercase w, and that's going to be over here, grains of moisture per pound of dry air. So remember, 7,000 grains equals a pound. Okay, so it's a way that we can quantify the amount of moisture in the air without getting some really, really tiny number. It's easier to keep track of our numbers that way. So it's grains per pound of dry air. And those are the units. Grains per pound of dry air, and there's 7,000 grains in a pound. And remember, a grain is just a drop of water. So it takes 7,000 drops of water to get a pound of water. And then we've got specific enthalpy. Which is here in BTUs per pound of dry air. So that's looking at the kinetic energy in dry air, how much energy the air molecules have, right? So we quantify that with temperature. We can look at the temperature between, the temperature difference between 2 points, okay? And we go up this line right here, and then we look at, between 75 and 85 degrees, that 10 degrees difference, you're going to have about 3 or 4 BTUs difference, okay, in those two quantities of air as far as the kinetic energy in the air. So you can quantify how much energy you have to remove from the air to get the sensible energy down, to get the temperature down. So again, that's over here, BTUs per pound of dry air. And that's H. Then we have specific volume, which is the inverse of density. So how much volume does the air take up per weight? Okay, so how much volume at a given temperature does a pound of air take up? Specific volume is here. So 14, 14.5, 15, and that's cubic feet per pound of air. So if I take a pound of air and I warm it up, what's the specific volume going to do?
Increase.
What'd you say?
Will it increase?
Yes. So when I warm up air, it gives more, it's got more kinetic energy. It's going to expand. So the volume is going to go up per pound of air. And, you know, the inverse of that is true. When you cool it down, a pound of air is going to have a smaller volume. So, and then we've got vapor pressure. Over here in inches of mercury. And that's inches of mercury. Hg is mercury. So I was talking to another student and they said it looked like I wrote IUTLG or something like that. So if you can't read my handwriting, ask me to repeat it or rewrite it or something. The units matter on this stuff. And you know, that's another way that we measure the amount of vapor in the air rather than relative humidity, which again depends on the temperature of the air, right? So, all right, so temperature and water vapor realities. So psychrometrics reveals the storage capacity of air to hold water at different temperatures, okay? So you can hold 4 times more water at room temperature than at freezing at 32 degrees Fahrenheit or 0 degrees Celsius. At room temp, you can hold 4 times more water. So, you know, warm air, again, has more energy in it, right? So the molecules are vibrating faster and they're further apart. You know, the same is true for water molecules, the moisture in the air, and it has more energy. It's further apart, right? The molecules are vibrating faster, so it's less dense. When water vapor cools down, it becomes dense. When air cools down, it becomes more dense. And when moist air cools down, it becomes more dense. The molecules get closer together. And the molecular structure of water is such that those water molecules want to grab onto one another. You know, you have to put a lot of energy into water to get it to boil, right? So, you know, water wants to stick to itself, right? So as it loses energy, it wants to grab onto, those molecules grab onto each other and they condense. And then you start to lose humidity in the air. And the rule of thumb here, for every 18 to 20 degrees Fahrenheit, you double the storage capacity for moisture in the air. It doubles every 18 to 20 degrees Fahrenheit. The storage capacity doubles. So say you have a leaky house, and this is going to be, let me get a straight edge. Maybe my drawing won't be quite so bad. Whoops. So I have a house, and this is my wall assembly. Oh, this is all right. Okay, this is the inside of my house. That's a little weird there, but it's okay. That's the inside of my house. Okay, so this is my wall assembly. So I've got insulation in there. I've got drywall over here or whatever, and you know, I've got my control layers. My sheetrock is my air control layer. I've got continuous insulation on the outside. I've got some sort of moisture control layer there. So if I have warm air inside my house, you know, there's all these water molecules in it or whatever, and I have a leak, you know, there's a hole, or, you know, somebody, when they put in the drywall, they didn't seal around the plug or something, you know, that electrical box. And so air, you know, the pressure is going to be higher in my house. If it's warm in my house and cold outside, the pressure is higher in my house and lower outside. The humidity is also higher in my house and lower outside, because cold air can hold less moisture than warm air, right? So if the pressure is higher, there's a positive pressure inside my house and a negative pressure outside relative to one another, air is going to want to go outside of my house, right? There's more energy in the air in my house, and energy travels from higher concentrations to lower concentrations. That pressure difference is going to, you know, push the air out of my house. And so if I have a leaky wall here and I've got warm, humid air, the air is going to go inside my wall and it's going to find a way to get outside. And say I didn't have exterior insulation, say I didn't have continuous insulation or something like that, and you know my sheathing is cold, and when that warm, humid air hits that sheathing and the sheathing is cold, the temperature of the sheathing is at or below the dew point for that warm, humid air, it's going to start to condense. It's going to be condensing inside my wall, and that's going to be bad, right? So we don't want that. So, you know, that's why it's important. Air sealing is really important, and you're, you know, drawing your control layers accurately and making sure that the design of your wall is good so you can control this kind of stuff. And you don't have a bunch of condensation in places where you don't want it. So again, here's that rule of thumb. For every 20 degrees Fahrenheit, you know, 32 to 50, 50, 72, so on, the moisture storage capacity of air doubles. Okay, so this gives you some idea. So, and you know, if we have like a crawl space or something, sort of the same things going on with that. You know, when you have a vented crawl space and no air conditioning in your house, back in the day, you know, when they insulated with newspaper or whatever they could find, or they didn't insulate at all, and they built their houses, you know, the foundation with stones, you know, their houses were super loose. They didn't air condition their houses. You know, the temperature inside the house and outside of the house was roughly the same. There wasn't that big of a difference. But as we make our houses tighter and as we start to cool the inside of our house, you know, it's back to the building as a system, right? You know, when it's cooler up here, and say if you're in a really warm, humid climate, you know, typically your crawl space is going to be cool, right? You don't have a ton of exterior facade exposed to the sun of your crawl space. But, you know, in a warm, humid climate, when you have a vented crawl space, that warm, humid air is coming in here and it's cycling, you know, air moves around, it's a fluid. So when it's cool up here and, you know, you don't have a sealed crawl space and you haven't put in, you know, this is a well-designed crawl space. You have foil-faced polyisocyanurate or foam with seams taped and sealed. And so that's, you know, that's sort of sealing this, sealing the underside of your floor, these engineered trusses or, you know, floor joists or whatever you have. You know, but if you don't have a control layer right there and you've just got, you know, these floor trusses are open to the crawl space, you just got bad insulation up in them. Bad insulation is just fiber, you know, air can pass through that. So when you have warm, humid air going up and getting against your floor and your air conditioning inside, it's cool out here and hot and humid out here, you know, that warm, humid air is going to get against the underside of your floor and the water is going to start to condense. You're going to start having water issues. You're going to have mold under there. If your air control is not well done, you know, and you have air passing in between your crawl space and the living space in your house, you know, and you have moldy air coming up, mold and dust and all that stuff's getting in your air and it's coming into your house, right? If you have air transfer between those two places, you know, and when it hits the cold surface, that subfloor, it's going to start to condense, and you have you have moisture sitting on your subfloor and your floor trusses, you know, over time your floor could start to rot or buckle, you know, and you're going to have issues with that. And again, this all goes back to the building as a system. When you remember grandma's house, when you make one change, like adding an air conditioner, you have to think about all the effects that it's going to have on the rest of the building, right? So, you know, we have to think about our buildings as a system and think about the whole picture. When we make one small change, we might get some adverse effects from that small change. This is a sling psychrometer. So it measures dry bulb, wet bulb, dew point, and all of these things are related, but you get dry bulb and wet bulb from your sling psychrometer. So here's your dry bulb. This is your dry bulb here, just a regular thermometer. Here's your wet bulb thermometer. It's got this little cloth on it. They put room temperature water on it and then sling it around. Okay. And this, you know, this works based off the premise that, you know, of the evaporative cooling process. So the drier the air, the more evaporation takes place. And when the water evaporates out of your wet bulb, it pulls energy out with it. Okay. So, you know, we get room temperature water, sling it around for a minute or something. The wet bulb will always be cooler. And then they use the dry bulb and the wet bulb temperature differences to make sort of inferences or to figure out some of these other parameters. You know, there's a direct relationship between those two things, or there's a correlation between these things. And you can watch a video on exactly how they do that stuff, and you know, there's good information online on that process for calculating these other parameters. But you know, that's what a sling psychrometer is. So we'll watch this video really quick. Are you guys following this stuff? Is everybody keeping up okay? Is it making sense? Maybe we'll save this video for the end of class if you guys are keeping up with it. Remember, rule of thumb, if you know 2 properties about air, you can find everything else about it. You just need 2 properties, right? So I think we've answered. Has everybody got all the answers for the quiz? I'm seeing a yes. I think we've pretty much answered them all at this point. I would like you guys to be able to use the psychrometric chart. I'm going to go over some examples. I haven't created quiz questions for that yet. It's not terribly difficult once you figure out how to do it. We'll watch this video before class ends, but I'll just work through these examples, and if it's making sense, you know, maybe you can watch that video later and we'll save some time. Maybe we can finish early or something. I'm not sure how long it's going to take to get through the rest of this stuff. So if we have 2 parameters of our air, we have two things that we know about the air. You know, if we have air that's 95 degrees Fahrenheit and relative humidity of 70, what else do we know about that air? And hopefully, yep, okay. So if we have a dry bulb temperature of 95 degrees Fahrenheit, so I'm right here on my dry bulb temperature on the sensible energy. Remember, this is sensible energy. This is latent energy. This is, you know, kinetic energy. And this is humidity, right? So I'm at 95 degrees Fahrenheit and 70% relative humidity. So I'll look for 70%. No, this is a bad example, sorry. So let's say we'll say I'm at 80 degrees Fahrenheit. I'm at 80 degrees Fahrenheit. And 70% relative humidity. So I'm at 70% over here. Hopefully these 2 lines intersect. They do. So what else do I know about this air? So at 70% relative humidity, 80 degrees dry bulb temp, I've got about 108, between 100 and 110 grains of moisture per pound of dry air. So remember, 7,000 grains is a pound. So I've only got, you know, I don't even have, well, no, I've got very little moisture in the air, okay? It's, you know, there's not much mass to it. My vapor pressure is, you know, somewhere between 0.7 and 0.75, something like that, inches of mercury. Okay. And I can go over here, look at how much kinetic energy I have. I have about 36 BTUs per pound of dry air, something like that. And when I do create these quiz questions, you can use, I'll try to, get these numbers pretty accurate, and make the tolerances on the answers a little bit wider, because some of this stuff is hard to read. But these are approximations. These are not exact, but this is a very useful tool, and for people to have in the field. You can tell a lot about air from this chart. So again, let's see, where's my wet bulb temperature? My wet bulb temperature at 80 degrees Fahrenheit and 70% relative humidity. My wet bulb temperature is like 70, I don't know, 72 or so. This is my wet bulb, between 70 and 75. Okay. My dew point is going to be, I'll just draw a line out here when I have, and that's changing my relative humidity. Remember, I'm going across my relative humidity lines, but I'm staying at that same humidity ratio. The moisture in the air is not changing. The relative humidity is changing, because as I move to the left, I'm dropping in temperature, I'm losing kinetic energy, and I hit like, I don't know, 69 degrees Fahrenheit or something, when I have 108 grains per pound, grains of moisture per pound of dry air, and I go from 80 degrees to 68 or 69 degrees, I'm going to start to lose moisture. The air is going to start to condense. The moisture is going to start to condense, and I'm losing moisture from that air. If I want to cool down even further and continue, if I want to get moisture out of the air, I have to go down. I have to continue to cool down and go down the dew point temperature. This is your dew point. This curved line is your dew point all the way down. So I have to go down, and I get to like 55 dew point. I'm at 55 degrees. And then my humidity ratio, I have like 65 grains per pound of dry air, something like that. Again, this is not super precise. And I think I covered everything. I skipped specific volume. My specific volume is right here. So if I'm still at 80 degrees Fahrenheit and 108 grains per pound of dry air, my specific volume is between 13.5 and 14 cubic feet per pound of dry air. So we'll call that like, I don't know, 13.95 or something like that. So does that make sense to everybody? Did everybody follow that? Did anyone follow that? Are you guys bored out of your minds? I'm seeing some answers yes. I know it's sort of early for this kind of stuff. We'll keep going. Again, you can always look back and look at the video. So if you're not following this stuff, we'll do a real world example, and maybe it'll help bring this stuff into a context that makes a little bit more sense. So this is a typical scenario that you're going to see in commercial HVAC systems. So you supply air to a space that's typically about 55 degrees Fahrenheit, and it's going to be at 95% relative humidity. So somewhere in there. So when we supply 55 degree Fahrenheit air, 95% relative humidity. Remember, this is dry bulb. We're feeding air into rooms where there are people. My happy, comfortable little person, because my HVAC design was done well. There are computers. He's working away. He's typing his little fingers away, trying to write his paper for his professor, who's demanding, makes him do all kinds of stuff. You know, you're getting heat off of this person, right? You're getting heat off of this computer. We've got equipment in our buildings. We've got water heaters, stuff like that. He's a bad student, and you know, he's being forced to hang out in the mechanical room where the water heater is. There's tons of heat gain and stuff like that in there. But when I have all these heat gains in the space and I send 55-degree air in there, it's going to mix with these heat gains. It's going to warm up, right? It's going to warm up to like 74 degrees Fahrenheit or something like that, okay? So I'm here and it's going to go over here. We're going to say it's like 70, 75. So what happens to your relative humidity? It goes down, right? So you send cool air that's going to be able to mix with your warm air in the space and get an end result of air that's comfortable. This guy's still pretty happy, even though he's having to do all this schoolwork. He's still pretty happy because he's comfortable. And the relative humidity came down, you know, and then it's going to continue to increase. So the temperature is going to go up even more. And, you know, when you have, say you're in a restaurant or something like that, or, you know, even at school, people are sources of pollutants, right? So when I breathe out, I expel moisture in my breath. I sweat, I perspire, you know, doors are opening and closing. It's humid outside. I'm getting moisture coming in. I don't know how to draw moisture. I'm getting moisture in from this guy, from, you know, if I'm in the cafeteria, from cooking, from boiling water, I'm getting vapor into the air, humidity from the outside. People are sweating, and the humidity is going to increase. So I'm going to increase in my absolute humidity. And, you know, so I have to, when I return that air that's got pollutants and more moisture in it and stuff like that, I have to take it back to the dew point and get that moisture out of there. I have to condition that air and cool it down to the dew point. And I want it back at like 50% or 95% relative humidity and 55 degrees Fahrenheit. So I want to be back right here. And so I'm condensing that moisture in the air. It's going across my heat exchanger in my HVAC system. Warm air hits a cold coil. That coil has an energy deficit, so that warm air gives up energy to that cold coil. The heat transfer fluid in that cold coil picks up that energy and carries it away to dump it somewhere else, right? Refrigeration cycle is how we cool buildings. So make sure I covered everything. Again, you know, this relates back to the building as a system, and we're looking at and we can do calculations and figure out how much energy, or, you know, how much energy we need to remove to cool our air, or how much energy, if we're looking at the latent energy, we can figure out how much energy we need to remove, right? If I have to go from 60 degrees on the dew point to 55 degrees on the dew point, I can say, how much energy do I have to take to get that temperature down per pound of dry air? You know, this is, what is this? 20, like 3 BTUs per pound of dry air, something like that. So, you know, this is bulk convective flow, and it's using bulk convective flow to add a cold air mass to the room, okay? And it cools down the warmer air that's already in the room. And this is how we control the relative humidity of the room. Does this make sense to you guys? Is everybody following? Anybody? Is anybody following? I see one thumbs up. Are you guys hate this? I think it's pretty interesting. Science, right? This is science. We're learning, we're having fun. I'm starting to have, I think I've hit my coffee limit, my caffeine limit, so sorry. But no, this stuff, I think this stuff's really cool. I love this stuff. So I hope you guys are not bored out of your gourds. If you are, sorry. So, you know, again, condensation typically occurs on the next cold surface, not so much in the insulation. So when we're looking at temperature change across an envelope, this is this is more or less what the temperature curve does, okay? Most of your temperature change happens across your insulation, all right? And this is, I think I mentioned before, our steady state conditions. We're not using calculus. When we do these heat transfer equations, we're sort of assuming an average temperature, like, you know, steady state. We're using, you know, 2 temperatures so we can get an approximation. You know, we're not using super complicated math, because this is, you know, this is about all we need to do to give ourselves a good idea of what's going on. So, you know, you have a simply constructed wall. You've got drywall. You've got drywall here. You've got cavity insulation. Your, you know, R19 bat or whatever it is. If you're in Boone, you've got sheathing, and you've got siding, right? So the temperature drop is happening here. That warm, humid air is coming in. You know, your dew point temperature could be here, but it's just in the air. It's not gonna just condense out of the air, right? It's gonna have to hit a cold surface. So it's not gonna condense until it hits your cold sheathing. You know, and remember, in psychrometrics, every 18 or 20 degrees doubles the amount of water, that doubles the amount of moisture that the air can hold. So, you know, if you've got a leak on the exterior and you have a leak on the interior, air is going to find its way through somehow. Okay, higher pressures inside relative to outside, higher moisture content, higher relative humidity. So at some point, you're going to hit the dew point temperature. And so remember, the dew point temperature could be right here, but it's not going to condense until it hits that cold surface. So you know, we can use the psychrometric chart to analyze our construction assemblies, right? Not only do we use it for figuring out, you know, energy and humidity in the air and HVAC design, but we can use it to analyze our construction assemblies. So say my dry bulb inside is 70 degrees Fahrenheit, and my relative humidity as a percentage is like upwards of 50%. So if I look at 70-degree air at 50%, let's see, where are we? 50% relative humidity. If I've got 70-degree air inside my house and it's, you know, even 40 degrees outside, 40 degrees Fahrenheit outside, what's my dew point? Somebody tell me what my dew point is when I have 55 grains per pound of dry air of moisture and I'm at 70 degrees Fahrenheit. What is my dew point? Anyone?
Is it around 50 degrees?
Yes. And what does that mean for condensation? What are the implications of having a 50-degree dew point when it's 40 degrees Fahrenheit outside? What temperature do you think your sheathing is going to be? What conclusions can you draw from the psychrometric chart in your wall design?
Is it going to be around that 50-degree dew point with condensation on it?
Yeah, but what does that mean for your wall? You know, if it's 40 degrees outside and you have an air leak, and if it's 40 degrees outside and your dew point is 50 degrees Fahrenheit, you have an air leak, and you're at like 70 degrees inside, so you got warm air going through your wall with 50% relative humidity. What are the implications of this? And maybe you said it and I just didn't understand you.
Once the air goes through the insulation and hits the cold exterior wall, it'll condense inside the
Bingo.
wall.
Bingo. And that's a problem, right? So we can use this to say, and remember, R value can be added like electrical circuits in series, like resistance in series. I think that's what it was. So if I have, and these are just numbers that I'm making up off the top of my head, but I have my sheetrock that's like, I don't know, 0.5 or something like that, or 1.5. We'll say it's 1.5. And then I have, my cavity insulation that's R19. And then I have, let's see, I have my moisture control layer, and that's got some R value probably, but it's negligible. And then I have XPS, and then I have my siding, or my cladding, whatever you want to call it. Sorry, this picture's terrible. When the temperature change across this, so my XPS is going to be like, I don't know, let's say it's about 10. I don't know off the top of my head what XPS is, but we'll say we've got 1.5 inches of XPS, and it's somewhere in the ballpark of 10. And then my sheathing is maybe I think wood is R1 per inch. So I've got, I don't know, 1/2 inch, something like that. And then my siding, we'll say it's another 0.5 or something like that. These are just made up numbers. So 19, 29, 30, 31.5. My wall is R31.5. So 70 degrees inside, 40 degrees outside. As that temperature changes across that wall, it is changing in relation to the change in R value. So it changes, it's linear. So as my R value begins to decrease, the temperature follows that same pattern. Does that make sense? We'll probably look at some formulas on this stuff and how to calculate. You can figure out like what percentage, and don't worry about this too much right now because I'm explaining this off the top of my head. I'll go into more detail in a video if we're going to do this stuff, but I can say what percentage of my overall R value is the first layer. So over 31.5. So my first layer this is the ratio of the R value of my first layer. Then my second layer is R19 over 31.5. So I can look at a percentage. And so if the temperature change is going to follow this percentage, the same percentage of R value that my layers make up, that's the same percentage of total temperature change that's going to occur across that layer. Does that make sense? Like I said, I'm explaining this stuff off the top of my head. So if it's not making sense, don't worry about it too much. But if I have my cavity insulation is 60% of my total insulation. So if I go 70 degrees to 40 degrees, 60% of that 30-degree temperature change is going to happen across this layer. So if I have a 30-degree temperature change, I'm going to lose 18 degrees across that layer. So I can predict about what temperature my air is going to be when it hits the sheathing. So I can look over here and say, all right, I started with 70-degree air and I'm at, 55 grains per pound of dry air, right? So I'm losing, let's see, most of my temperature change is happening across that. So let's just go ahead and say I'm losing, 18 degrees across that. So 70 to about 50. I'm already at the dew point right there. That's probably not a good thing, right? 70 minus roughly 20, 50. Yeah. So my sheathing is already getting close to the dew point. So maybe I want to add some more insulation or something, you know, and it depends on a lot of factors as far as how you design your wall. So, you know, we'll go into this stuff in more detail later, I think. But that's, you know, that's another thing that you can use the psychrometric chart for. Did everybody understand that? Did that make sense? I'm seeing some nods. Yes. Cool. Great. Again, you know, that exterior insulation, and you know, all those numbers were made up. So that may not be a real world scenario, just made up numbers off the top of my head. But you know, when you add exterior insulation, you can shift where the dew point is. And if you have good air control layers and stuff like that, you know, and good moisture control layers, you can avoid some of these issues. So I added exterior insulation. So instead of at the sheathing, I have continuous insulation out here. You know, I don't have any thermal bridges, which I guess this is the class you're supposed to learn that in. So maybe you don't know what a thermal bridge is yet, but we'll talk about that later. You know, but if my moisture control layer is here and I shift the condensation point to right here, even if it condenses, if it's outside the moisture control layer, it's not a problem, right? But it also reduces drying potential to the outside. So if I rush the construction process, if I have a bunch of rain, you know, before I get my house totally dried in and all of my wood's saturated, and then I have to dry it in real fast, and then I get pushed and I have to, you know, go ahead and do some of the finishing work on the inside, and I trap a bunch of moisture in here, and you know, I've done a really good job sealing all of that stuff up. That moisture is not really going to have anywhere to go, or it's going to have somewhere to go, but it's not going to be able to dry out fast enough, and then I'm going to start having issues. So another tool that we can use is something called Woofy. And this is, I know this is hard to, this is sort of a hard thing to understand when you're looking at this. When you use the software, it makes more sense. Okay, so when I use this software, I input my control layers, I input my construction assembly. I'm gonna have a line here. If you can see that for my drywall, I'm gonna have a line that starts here for my cavity insulation, and I'm gonna have a thickness associated with that. And so that line is gonna stop over here. That's gonna represent my cavity insulation. And then I'm gonna have a line for my vapor control layer, and then for my exterior insulation, and then for my siding, and so on. And so this tells us, this line right here tells us, if you can see that, that line, this red line, this dark red line tells us where the temperature is across our envelope at any given time. And this sort of shaded area tells us the history of where that temperature has been. Down here, we're looking at water content in kilograms per meter cubed. So here's my line across that same envelope, and you're gonna have your dew point over here somewhere, I think, relative humidity. You've got your relative humidity, that's what it is. So you've got your relative humidity here, and it's telling you, this is sort of the history of where your relative humidity is, but this green line here is telling you where your relative humidity is at any given point in your wall assembly. Okay, so you can say, you know, up here, my relative humidity is really high, but that's inside of my building. Here, my relative humidity is just over 60. I might be okay there depending on the temperature outside. And then here, you know, it's dropping down. But this is just a tool. It's called Woofy. You can get a free version of this, I think, and play with it a little bit and get a better idea for it. But if you're interested in doing, you know, commercial building envelope consulting or building forensics or something like that, you know, this is something that design firms will use, engineering design firms will use to evaluate building envelope design and see where you're at, and try to use this tool in conjunction with other tools to evaluate building envelope design. stuff like that. So if you're interested in any of that stuff, you know, check out Woofy. It's a pretty cool tool. And again, it shows you over time, and it's got like a weather file that you can put in there, and it's using real data, real historical data, and will show you, you know, it's got all these algorithms and stuff built into it, and it'll show you based on your location what the temperature and the humidity is doing based on your design. So it's a pretty cool tool to use. We're almost to the end of today's lecture, so I'm gonna see what else I've got in here. Here's that thing that I was talking about, using, you know, that ratio between your R value. We'll just go over this really quick. And this is in the ASHRAE handbook, chapter 25, section 6.1. This is sort of how you calculate where your temperature is going to be based on what section of your building envelope you're going to be. Okay, so the temperature at the back of your sheathing, the temperature at your sheathing on the exterior of your building is going to be this equation. It's going to be the temperature inside minus the temperature difference, and then times this ratio of how much your R value changes from temperature from your inside to your outside, or to the outside, and to this point. So this is your total R value. This is your cavity, you know, the R value up to that cavity, the backside of the cavity insulation, backside of your sheathing. And it's going to tell you about what the temperature is going to be at the back of your sheathing. And you can look at the psychrometric chart and figure out what your relative humidity is at that point and what your dew point is going to be.